In this video, I will explain the diagonal argument. This is an important method for dealing with infinite sets, and it is a crucial technique in modern mathematics and logic research. The way of thinking related to the diagonal argument is the content of this video. So what is the diagonal argument? One reason set theory is important in modern mathematics is that it provides a way to deal with infinity. And in set theory, the basic method to handle infinity mathematically is one-to-one correspondence, as explained in this video. However, one-to-one correspondence is just a method to show that the sizes of infinite sets are the same. What happens if the sizes of two infinite sets are different? In this case, we use the diagonal argument. In other words, the diagonal argument is a method to show that the sizes of infinite sets are different. Cantor's diagonal argument. Let's first take a textbook-like look at its content. We'll start by examining the conclusion, and then I will explain the thinking process behind this argument. The starting point of the diagonal argument, in other words, the question is this: which is greater in number, natural numbers, or real numbers? Here, there is the issue that both natural numbers and real numbers have an infinite count. Whether finite or infinite, to compare the counts, you have to establish a one-to-one correspondence. Even if you don't fully understand this video, with a little thought, you can realize that the very act of comparing involves one-to-one correspondence. Anyway, let's start with one-to-one correspondence. First, if you think about a way to establish a one-to-one correspondence between natural numbers and real numbers, it's quite tricky. While studying set theory, you can see a method that proves that the number of natural numbers and rational numbers, that is, fractions, are the same. Seeing that, you can realize that it's not something anyone can easily do. Finding a way to establish a one-to-one correspondence requires a significant amount of creativity. In other words, if you consider this not from the perspective of already knowing the diagonal argument, but from Cantor's perspective, when he was first comparing the counts of natural numbers and real numbers, when you can't establish a one-to-one correspondence between natural numbers and real numbers, you wouldn't know whether you can't find a one-to-one correspondence because there is one, and you just haven't found it, or you can't find it because there isn't such correspondence. Here begins the creativity of Cantor that marks a milestone in the history of mathematics. From a results-oriented standpoint, the starting point is this. In other words, since we don't know whether one-to-one correspondence is possible or not, for now, we assume that natural numbers and real numbers can be put into a one-to-one correspondence. Assuming it means that we are making this assumption 1. The plan in mind is to try assumption 1, that is to assume that a one-to-one correspondence does exist, and if there is a problem with this, the conclusion will go to point 2. It's a reductio ad absurdum approach. First, we have to find a way to establish a rough one-to-one correspondence between natural numbers and real numbers. That way is like this. Here, this part can be considered as an arrangement of natural numbers in a vertical list. Why didn't I label them as 1, 2, 3 and instead used S? That's because we are naming the real numbers, and it's a technical detail. To avoid unnecessary complications, think of them as needlessly labeled S1, S2, S3 instead of simply 1, 2, 3. Though it may be needless to add an S, it doesn't cause any problems. And this is a list of real numbers. The real numbers listed here are based on the definition of real numbers. That is, real numbers can be expressed as non-recurring infinite decimals. Up to this point, it may not seem particularly remarkable, but understanding that significant creativity was needed to prove this for the first time will make mathematics more interesting. Up to here, we have assumed that the number of natural numbers and real numbers is the same. The next part is the most creative idea. Now, in the realm of real numbers, we find the missing number. That is, we assumed that there was a one-to-one correspondence with natural numbers, and now we identify the number that was not accounted for in that correspondence. The key is how to find it, and in this domain we transform the numbers diagonally to find it. That is this number. In this case, we created a new number by adding 1 to each digit. That is, since this is a 0, we change it to 1 and place it here. And since this is a 1, we change it to 2 and place it here. We continue doing this. If a 9 appears, we change it to 0 and place it in that position. Now let's think about this number. This number has two characteristics. First, it's one of the ordinary real numbers that should be in the set if we assume a one-to-one correspondence with natural numbers. But the second feature is that it is different from any number that has already been put into a one-to-one correspondence, so it's the ordinary real number that's missing from there. In summary, when we assumed that the number of natural numbers and real numbers is the same, meaning that a one-to-one correspondence is established, we found that there are real numbers left that do not correspond. So what if we put this number back into the set and rearrange it for one-to-one correspondence again? You could still find another uncorresponding number using the same method, right? Ultimately, in the diagonal argument, it not only shows a method to find a single uncorresponding real number, but by repeating the same method, it also shows that you can find infinitely many uncorresponding real numbers. Therefore, the conclusion is that the number of real numbers is greater than the number of natural numbers. No matter how hard you try, it becomes evident that a one-to-one correspondence between natural numbers and real numbers is not possible, and there are remaining real numbers that do not correspond. Well, let's not stop here and dig a little deeper for a better understanding. Here it might sound silly, but shouldn't we also consider the possibility that there might be missing numbers in the natural numbers as well when it comes to one-to-one correspondence with real numbers? Such seemingly foolish thoughts are absolutely essential for precisely understanding mathematics. Professors usually skip this part, expecting that students will think this through and find the answers on their own. It's not that they skip it because it's unnecessary to explain. Again, let's think about whether there are missing numbers in the natural numbers when it comes to one-to-one correspondence. The starting point of this thought should be the same as before, starting from here. This is assuming that everything has been mapped one-to-one without any omissions. So, we should be able to find any missing numbers from here, but there is no way to do that. Could it be that there is a way to do it, but we just don't know it yet? To confirm this, let's think about the reason why we were able to find a new number in the realm of real numbers. This was possible because in the realm of real numbers, there is infinity in two directions. Firstly, the number of real numbers is infinite in this direction. And in fact, the number of natural numbers is also infinite in this direction. However, real numbers are also infinite in this direction. That is, they are non-repeating infinite decimals. So each real number contains an attribute of infinity within it. Upon reflection, you'll realize that this second form of infinity is the source that enables us to find new real numbers through the diagonal argument. However, in natural numbers, there is no such second form of infinity. That is, there is no infinity within each individual natural number. As a result, when we assume that natural numbers and real numbers can be put into a one-to-one correspondence, there is no way to escape using the diagonal argument in the case of natural numbers. In this way, I have elaborated on the mathematically important aspects of the diagonal argument. The diagonal argument later becomes an important technique in mathematics and logic for proving something with infinitely many elements. If this video was helpful, please hit the like and subscribe button and turn on notifications. Thank you.